Sorry, Dan,
Yeah,
I
at some
hijacked
point.
your...
It's alright, no worries.
I'm not sure who's going to initially, but yeah, probably Sam, Peter.
All good? Cool, right, I will begin. So, this is the penultimate lecture in the series. These last two lectures are now sort of less, practical on, sort of less demonstration and getting through Proteus, and more about kind of like finishing off the circle. And so this, we're going to be focusing on predominantly ordering, so the process of ordering, how to generate your bomb, and all the effort that you put in previously is now going to pay for when you generate your bomb, because it's essentially one click of a button, as opposed to having to pick all your parts out and, find them on find out, that kind of thing. We're going to go through a little bit of amplifier analysis in terms of understanding the performance of one. So there are obviously many ways to do that, but we'll only go through one of them. And then I'll do a quick demo of JLC PCB, so you can just see the process get done once through. It's quite simple once you've done it. There's just a couple of things that you need to watch out for when you're doing that. Okay, so evaluating the performance of an amplifier. So there are many different properties that you can analyze and go through. There's even more than this list. You recognise some, you won't understand others yet. But since we're building a headphone amplifier, I thought during the next week's kind of like demo, it would be good to actually attempt to take one of these measurements, and you can see how that's done as well. So instead of just saying, stick that pair of headphones on, look, you can hear music, it's well loud, sort of thing, you can actually see the performance of it, especially when you're in Class B and Class AB modes. That's the theory. So I'm going to have a quick look over THD plus N. So does anyone know what THD stands for?
Harmonic distortion.
Yes, well done. N?
I don't know what that is.
No? Anyone guess?
Noise?
Noise. Yes, exactly. Total harmonic distortion and noise. So I will explain what that means in the next slide, but for now we're going to have a look at these two charts. These two charts display exactly the same information. They both show you a 1 kilohertz sine wave. Has everybody seen the one on the right before?
Yeah.
Has anybody not seen the one on the right before? Okay, cool. So we've got a time domain chart on the left, and we've got a frequency domain chart on the right. Now, the frequency domain chart tells you the power of each frequency within the time domain chart across the bandwidth that you can see along the x-axis. So the x-axis is frequency on the right, the x-axis is time on the left. So time series charts are good for things like observing the overall shape of a waveform to understand what's going on. We are sort of temporal beings. We understand time as it flows, and that's what that screen looks like. It looks like a flow of time from left to right. You can see things like transient elements, spurious behavior on a signal. You can see bursts of noise, that kind of thing, quite easily. You can see timing between events on an oscilloscope. Everyone knows kind of how useful an oscilloscope is when you're doing this kind of thing. Frequency domain. So you carry out this thing called an FFT, and I'll give you a visual representation of what an FFT is in the next slide. But in here, you can see things like low-level distortion. So if I show you this, the voltage levels down here is extremely low, and as compared to the voltage at the top here. Bear in mind, this is a decibel scale. It's a logarithmic scale. This is a slightly lesser intuitive graph to understand until you kind of grasp what it is, and I think the next slide will do that for you. But just an example, 10 dBV is 10 dB voltage. That would equate to about 3.16 volts. Okay, so at the top, 10 dBV is about 3.16 volts per graticule. At the bottom, we've got minus 160 dBV, that equates to 10 nanovolts. So on the same scale, you can see the difference between sort of, 5 to 10 volts at the top, and at the same, taking up the same amount of distance at the bottom, you're at the nanovolt scale. Just to give a sense of scale, the difference between 5 volts and 5 nanovolts is a billion. You can fit a billion nanovolts into a volt. So how do you obtain this? So there's an animation on the left, okay? So you've got essentially a square wave. Every electrical wave, every time domain wave can be made up by a sum of sines. That theory is really important. These sines are kind of like, as it's being shown to you, when you sum all those together, that's what creates that original waveform. And then this is kind of the NFT. This is the FFT that you end up with. So obviously there's no noise floor on here, it's a perfect sinusoidal signal, but the theory is here. So like I say, every single time domain waveform can be made up by a sum of sines. The FFT transformation extracts those sine waves from the time domain signal. So you have to send an FFT algorithm a bunch of data. So you sample, generate all this voltage data, put it into an FFT algorithm, and then it'll convert that into this chart on the right. So what is this good for? Again, that's just that, that.
A really good graphic.
Yeah, it's good, isn't it? Because it kind of like gives you a visual understanding of what an FFT is, and you've got essentially both charts side by side as well. So what's it useful for? So in terms of THD plus N, so this is one important parameter of amplifier performance. Harmonic content is generated in nonlinear amplification. So devices like transistors, when they're in the nonlinear range, they will generate harmonic distortion, which is an integer multiple of the fundamental frequency. If the fundamental frequency is 1 kilohertz, what are the integer multiples of 1 kilohertz? It's really easy when you, it's wordy.
2, 4.
2.
Oh yeah, 3.
All of them. So integer multiples is just every single 1, 2, 3, 4, 5 times, 6, 7, 8, 9 times. Every integer multiple of the fundamental is classed as a harmonic. And actually, the graph on the right here, you see it says half, a third, a quarter, but you can see that the frequency is doubling. These are all harmonics. If you add an infinite amount of harmonics together, you'd get an infinitely perfect square wave. That's what would happen. And you can see on this graph, this is real data. You've got 1 kilohertz fundamental that they're feeding into the amplifier, but then they're reading back 2, 3, 4, 5 kilohertz, all these fundamentals. All of these harmonics. So if you want to assess how well an amplifier is in terms of its distortion that it adds to a signal, undesirable distortion, how do you do it? So you put a perfect sine wave in, and then you notch the signal back out once you're reading it back. So you'd get rid of this fundamental entirely with a notch filter. You'd band limit it across the bandwidth that you're interested in. For audio, it's 20 hertz to 20 kilohertz. And then you'd feed the rest of it. So you can imagine this. Imagine that's been deleted, and you've essentially got the rest of this stuff left over. That would then go into an RMS voltage, voltage measurement, and then that would give you the RMS value of the distortion noise that's left over. Next week, I'll demonstrate this live technique with hopefully our headphone amplifier, a simple sound card, and a bit of software, and you can actually see what the FFT looks like. So it's actually, when you see this thing, it's actually it's a lot more intuitive. It's lots easier to understand. Cool, right, so I am going to explain a little bit about design rules. I'll show you how to generate your Gerbers and BOM, and then I'll do a quick demo on JLC PCB. So design rules. What we should have done, and what you would usually do, is you sort your design rules out before you start laying a board out, because when you're designing, you know, features on a PCB that are very small, or you know, many layers, then your design rules will start to come into effect. A design rule are things that you can't violate because the fab house can't create it for you. So, for example, this is what Proteus looks like when you've violated a design rule. I've put a track that's too close to this through-hole pad, and if you get them far too close, then the fab house might just short it. And so you can set up Proteus to your specific fab house, you know, so that they're both kind of aligned with each other, and you don't create invalid schematics. And in Proteus, this is what it looks like. So there's a window called Design Rule Manager, and you just set your rules here. So Proteus only got a few rules to set. It's quite simple, and then obviously you pick these numbers up off JLC PCB website. You can find there, and all PCB manufacturers will either tell you them or they'll be on the website. So you go onto their capabilities area, read through it, and then put it in Proteus. I didn't mention this last week because the default design rules of Proteus are, where are they? Yeah, the 10 thou. You've got 10 thou minimum distances. That's big enough that will suit every single fab house that you'll go to. It's very generous, so that's why I didn't go through it last week. Okay, so BOM, Gerber's, and JLC PCB demo. Let's do that. Cool. So we've created our schematic. We've finished our layout, and we want to get this thing made now. Because you've put the effort in to create these parts and added all of this information, generating the BOM now becomes a very, very easy task. So the bill of materials button's here, the little $sign on it, click it. You'll be presented with a page that looks like the default template like this, but I've already modified this one, so I'm going to demo it on the rustic style. The fields down here are the columns that appear on the BOM. So you could have a discussion with your manufacturers and say, what do you want to know about about what information you need? But generally, the ones that I'm going to show you will do for everything. Stock code, we don't have stock code. We've actually called ours something differently. So if you go into the part, we've got stockist and stockist part number. And unit cost, we haven't really put our costs in either because they fluctuate. I mean, this year has been absolutely horrendous for the chip shortage and stuff, so arguably not that worth it.
Doesn't seem like there's a way to do price breaks either.
Yeah, good point. Yeah. So the way that I would advise is to get rid of these two and then start adding the ones that we would usually have. And
you have to click new and then add it up there somewhere.
Where?
If you go on where you just were and you go new.
Is it not?
New on the
Yeah,
right.
yeah.
Yeah, and you just type the stockist in there and it'll come up.
Yeah, when I run through this, before, I didn't need to do that, but yeah, okay. I guess when you're doing it for the first time, you will need to do that. So find the ones that you want. I always put tolerance in there, actually. That's a useful one, especially for your generic resistors. So new tolerance. Manufacturer part num. I have to add one by one like that. Those two are always useful, actually vital. We'll have stockist. Oh, that one's already in here. And Oh.
You've already done it.
Oh yeah, sorry. Nice one. Stockiest part number, and I think that'll cover us. Actually, I do put the special column in as well, because you might have put something in there that for the generic part, the assembly guys might need to know about. So you've got all your columns, and they now appear in the BOM. So the one thing that you want to check for when you're at this stage is, do you see anything on there that says not checked? You know that the script that we have, it has not checked by default. That means that you've not checked that particular thing. So if you've got any not checked on that screen, then you know that you go back into the part, check it, put a dash if you don't need it. But that's that. I mean, that's your BOM done now. It's literally, that's where a lot of that previous effort comes into play. So to export it, you've got a PDF option.
How do you modify it to look like the one you had before?
You would just do it on the default template. Because I think it's in the style.
Oh, I see.
But the easiest way is just to do it on the default one. Can you see I've already done it on this, so I wouldn't be demonstrating anything.
Yeah.
So, yeah, that's how you do it. But I mean, obviously, or you can edit the style and just make it how you want it to look. So you can export via PDF, or you can export via CSV, or actually into an Excel spreadsheet. You choose however you want to do it. You good? Yeah. Right, so we're happy with that. Cool. So the next thing we want to do is generate our Gerbers. Now, you could just jump in and start generating Gerbers. However, JLC want you to do it in a very specific way. This is one of the things that I kind of wanted to sort of tell you about before you start doing it all, and then you have to redo it all, because that's what would happen. Because I've done it even. I know about this, and I still make the mistake sometimes. So JLC want you to generate the Gerbers in a specific way so that it works with their server-side software when they're checking the Gerbers online. Because this is an online service, you can upload your Gerber files to the website, they analyze it, and then they'll post your circuit boards in a few days. I mean, it is an amazing service. It allows us engineers to get prototypes made, and you could just, play with it. This is, really, really, really good, because otherwise you'd be paying hundreds of pounds for a panel. But to get JLC to understand the Proteus Gerbers, what I would recommend to do is read through this entire article carefully. All I did was Google JLC PCB, Proteus, Gerbers, and it was the first result, it was the first hit. I'm not going to read through the whole thing specifically now, but I will show you a couple of the things that you need to do before you generate. The first thing is their board edge. They don't like the default board edge that appears on all layers, because this board edge actually appears on all layers by default. What they want is they want a watertight graphic on the MEC1 layer, and they tell you this in the article. And they don't want you to include the board edge either when you're generating your Gerbers. So what does that look like? So what you need to do is you've got your finished schematic, you've got your board edge, copy and paste it, stick it literally anywhere, and then right click it, and then change the layer to MEC1. So that's now on the correct layer, and now we're going to align it. So double click the existing one, and you see it's 38mm by -17.5. Double click that. 38mm by -17.5mm. So now I've got those two graphics on top of each other on different layers. I'm going to leave them both there because we've got them both. But when I generate the Gerbers, I'm going to exclude the board edge layer. The reason why I'm leaving them both is because Proteus doesn't like it when you don't have its own board edge on its schematic, because when it does all of its checking and stuff, it wants that board edge to be there, and I'll show you what that means. So we're happy now that this is going to be reasonable for JLC to use. So the way to generate your Gerbers is you go to Output, generate. It tells you that the layout's been modified, so you always want to run your pre-production check. So click yes, and this checks for lots of things, including you haven't got any zones that overlap, all your components are placed, all your nets are connected together. It just does a very basic check on everything to make sure that your schematic is as it should be. Your layout is equivalent to your schematic, should I say. Right, and then we've got this window that tells you essentially Gerber options. So you go back to JLC and then you check. This is the old version of Proteus, this is the new version of Proteus. And then, because I know these things off by heart, I'm just going to go through it. But we don't want our assembly layers, we don't want the board edge, that's an important one. I've used Mech 4 to put these dimensions stuff on. So if you want to draw things on your schematic, like what the profiles of like corners look like, or edge connector radiuses and graphic stuff, you can put it on one of the Mech layers. Avoid Mech 1, but also when I'm generating the Gerbers, I'm not going to include that stuff either because they don't want to know that. It's going to tell me to overwrite because I've already done this before, but it'll just work for you. And then it'll also say that it doesn't like the output formats it should have done. Let me just double check. RS2, I think I've got that option right. Yeah, okay, so it wants me to put this RS274X. And when you do that, oh, hang on a minute. Did I set the right layers? Sorry, one sec. Generate. I didn't. So no assemblies, no edge, no Mech 4. I do want that. And everything else is good. I'm going to run the Gerber viewer when done, just to show you. Delete that one, and now it should pop up with a thing that says, because I've changed the format of the Gerbers, it can't re-export it reliably. We don't care about that. It's just, you're not going to need to re-export it. And then the Gerber viewer, you can view the actual Gerbers. So choose the layers that you want to see. I'm just going to look at all of them, and then press OK. Now this opens a completely different tab. This information is nothing to do with, well, it's related, but the project information, the project data here is not the same as this data here. This data here is exactly what's going to be made by the fabrication house. This is pure Gerber data. So this is kind of this is what you'd want to analyze and check. So you can turn your layers on, and it doesn't have any concept of the net list or anything like that. Now, what I would do at this stage, what I'd recommend is I would print it on a piece of paper. So turn your edge on. It's not edge, is it? Turn your Mech 1 on, maybe copper 1. I think the drill holes, are the drill holes there? Mounting holes, okay. And then when you go to actually print it, I don't think you need to print it from the Gerber view. You can print it from the PCB layout as well. I think you can choose which layers, yeah. That's the board itself on an A4 piece of paper. You can choose the layers that you want. The drill layer is already included. But what this does is it gives you a physical copy of the actual board itself initially. You can then go and put it in the box that it's going to go in. You can slide it into a machine that it's going to go in on a piece of card or something. You can check a lot of things if you just print the thing off. You can see if you've done any user interface stuff wrong as well. So I'd definitely recommend doing that. So then we are ready to actually go into JLC and actually get the board created. And the way that you do that is we're on the main page. I always go down to this part and then select the layer count. So quoting for 4 and 6 layers. Now you can add your Gerber file, and if you've got everything right, this should just work. How to tempt fate. I've obviously exported all of my Gerbers not as a single CAD/CAM file. End of class 4. Yeah, so I'll tell you what I've done wrong so that you don't do the same thing. Output, generate Gerbers. I didn't select this. Output to a single zip file. If you don't, it's going to splurge all of the text files all over the directory that your project's in. So make sure that's selected. How many times do I need to do the same thing?
Depends on the fab from it, doesn't it? 'Cause I've had a few fabs where they don't want them all separate.
Yeah.
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 Mech 4 get rid. Right, is that right now? Is it? We'll find out. Delete that. Yes, please. Okay. Is it here? That looks about right to me. 9:58.
Time looks good, yeah.
Yeah, good. Good, we got there. Right. So this is quite good. It's quite this is what you get when you use these online fabrication places. You've got the thing as it'll look now. You know that you've done the board edge right. It's not going to throw an error, but what it won't do is fill in your dimensions properly. So if these dimensions still say 0, 0, you've done your board edge thing wrong. So what we'll do is we'll go through some options before you order, because some of these options can be a bit confusing if you don't know what they are. 4 layers, it's already been selected because it knows the layer count. The minimum quantity is 5 PCBs for $8.
The material, base material, is it always at F?
Ah, yes, good question. Good question.
But yeah, I know that, yeah, $8 for 5 boards is shocking.
That's crazy.
I didn't want to take away from that, but...
Yeah, no, it's a good point. So, FR4 is like a fiberglass material that almost all circuit boards are made out of. So the kind of like the dielectric substrate. You can make them out of aluminium, and also if you don't understand sort of like an option, you can hover over the question mark. As it says, aluminium boards have a better heat dissipation and thermal transfer than standard FR4, and also their impedance is going to be entirely different to FR4 as well. So if you're doing any impedance matching traces and that kind of thing, you'd need to be very aware of what the substrate is. But aluminium boards, you find them in like, you know, mains spotlights and stuff. You know, the little packages.
Do you find on the back of an LED?
That's what I mean. Yeah.
Yeah. Okay.
Yeah.
Because the heat dissipates.
Yeah. So you got essentially like a built-in heatsink. Yeah. So your LEDs are soldered to these,
Yes. Yeah.
and then that's somehow connected to the fins around the outside of it. Is it GU10 bulbs, something like that?
You also get the dirt cheap alternative of layers of paper. You've not seen that. If you were buying some peak cheap electronics, they have a like compressed paper dielectric in the middle.
Really?
Yeah, you don't want to use that if you ever see it as well.
Jesus Christ!
Just
I
never use it.
didn't even know you could get that.
I was just going to say that PCBs have turned up. If you want me to go get them.
They have.
Yeah.
Wicked.
Do you want me to go grab them quick? Someone else for you as well?
I will grab it afterwards.
Yeah.
I'll grab them afterwards. So that's me. My flag is now pinned to the mast for next week, isn't it? I better get these circuits working. So what you're saying, Joe, is that we should have an option for paper here, right?
Well,
Yeah, definitely not.
And the $4 a price. Yeah.
Yeah. An interesting thing about FR4, if we scroll down, get my head of myself a little bit here. However, material type, you can see you've got 2 different types of FR4 here. You've got like a high temperature version and a lower temperature version. I've not actually seen what that looks like on the... Yeah, it disappears when you click the aluminium radio. Cool, right, so layers. Obviously it's 4 layers, that's what we've designed for. We've uploaded the Gerbers for that. It's picked up the dimensions of it. There's 5 of them, that's the minimum. Or you could get 80,000 if you're really confident that it's going to work. Please prototype PCB first. Fair enough. I'd take that advice. Different design. So if you've got different designs on the same panel, you can upload, or if this contains different circuit boards, you specify that. Delivery format single PCB. So the PCBs are going to be chopped up and delivered in a package. Or if you've uploaded a panel-sized thing there, a panel-sized Gerber, you can do that. Or you can ask JLC PCB to put them in a panel as well. If they're in a panel, you can use your, what are they called? The silk screening, not silk screening.
Template.
Yeah, the stencil, yeah, to solder them up. So you've got a big metal stencil, put some solder paste over it, like a squeegee, and take the stencil off, and then you can just place all the components on a big panel. Rather than doing tiny little boards at a time, it would take a long time.
Good for a bed of nails sort of test rig.
Yes, yeah, exactly. Thickness, standard PCB thickness is 1.6 mil. If you need to go thinner or thicker, you'll know the reasons why for that particular board. 2 mil, it would be a pretty 2 mil 4 layers would be pretty rigid. Impedance, we're not impedance sensitive on our design, but if you're doing high speed traces, differential lines, that kind of thing, you will be. You have to fill in your layer sequence. So top layer is top copper. Inner layer is inner 1. Inner layer 2 is inner 2, which is actually layer 3. And then the bottom layer, which is layer 4, is bottom copper. So you need to make sure that you fill that lot in. Now you can have whatever colour you want. Purple's new. It looks quite nice, doesn't it?
But don't pick black or white unless you really hate yourself.
Trying to find and debug traces on a black silk screen is a royal pain in the arse.
Red's a good one.
White's also horrendous.
Red's quite good if you're making a prototype board. Well, it's not necessarily relevant here, but if you're in industry, you might do a red board for your prototype and a green board for your production runs.
Yeah. I think it's a silk screen. Did I say silk screen? I meant solder resist. Yeah. Yellow? Ooh. Blue? Blue's quite, yeah.
So is that why Apple doesn't have anything black? So you've got no.
Yeah. So it's like when you see those cars in camo, the new production around the Nürburgring. Yeah. And then you've only got one option for silk screen, so you'll have a white silk screen.
Why?
That would just, oh,
No.
I say that. But you do, if you choose weird options, it does tell you that you've got a weird option, and then you get like a weird special process fee addition
So
in
does it add extra for red then?
I
Oh yeah, $18 for red.
yeah. There you go.
People do purple quite common though.
Well, it's new. It's brand new. So I think they've just put it on their promo because
Yeah. Why not?
yeah.
Look, it's your mother's. You've got cheap taste.
Okay, so surface finish. Does everyone or does anybody not know what surface finish relates to?
No,
You do know or don't know?
I don't know.
You don't know. Okay, so that's the how the exposed copper, pads and features of the PCB are treated before they come to you. Because you don't get, if you get a PCB, you don't just have a raw copper exposed on the pads and on the through hole and the vias and stuff. They're always treated because copper tarnishes extremely easily. So these, you've got essentially two options here. There are more options with different fab houses, but the two main options here is Hassel, hot air level soldered, hot air solder level. Use a solder, hot air levels it. This is with leaded solder, and that's with lead-free solder. Unfortunately, their lead-free option does add the special process fee as well, which is a bit annoying, really.
Do you think we should be going lead free?
For the surface finish, it doesn't really matter that much. The amount of lead exposure, but it actually depends if you're going to be ROSH compliant or not.
Okay.
If you're ROSH compliant, then you'll have to choose lead-free solder, or you choose Yep, and this one is electroplated nickel immersion gold.
That sounds expensive.
It sounds expensive. It's not mega expensive. It's an extra $15 on the 5 boards that you've got. They, as in the name, it says they electroplate nickel onto the copper first, and then they immerse that into gold, the gold solution, and then the gold sticks to the pads. This does actually produce very good looking PCBs. But it's not just for looks, because as soon as you solder all over it, you don't see it. Gold doesn't tarnish at all. And if you get this other finish called hard gold, you get a thicker layer of gold onto the surfaces, and that's good for things like contacts, because you don't abrade, you know, there's no abrasion, very little abrasion, because it's...
Sure, so like you've got the fins where you're plugging a board in and you've got the, like,
Yeah, if that's a hard gold finish, then it's very reliable. But it's, for us, standard hot air, soldered, levelled with lead will be fine. So the outer copper weight. So the copper weight is actually the copper thickness. I think is it 35 microns for 1 ounce? So, I don't know why they use these units.
It's an ounce per square foot, isn't it?
Yeah, but is that what it is? An ounce per square foot?
So they'll evaporate if it's like an ounce per square foot of copper on the board or something.
Yeah.
I think,
Yeah. So that's what. Yeah. So that's the units you have to deal with. You would typically use 1 ounce on your outer layers. If you need to jump up to 2 ounces, you'll know why, because you might have traces that are carrying more current. So you need more copper on there. There's a lot of other things you can do to get around that as well. You can use wires as bus bars. You can actually use bus bars. You can actually chop away the solder resist along the thicker tracks, so that when you come to wave solder it, you just get a load of extra solder deposited on the track, and that decreases the resistance of the track. It's a very cheap way of doing it as well. So that's that. Inner copper weight, 1/2 ounce. That's very typical. I've never known inner layers to be 2 ounces thick. Yeah, I don't know why the option's there. Maybe there's some situations where it can be.
Does it become an option if you press the 2 ounce?
I reckon you need a thicker board for it to be 2 ounce.
Aluminium for 2 ounce.
It's gone.
It doesn't give you an inner option on aluminium.
Yeah, don't know. It's not usual anyway. There's a program. I've not got it installed. I'd have shown you. I'll show you next week. There's a program called Saturn PCB Tools. Has anybody heard of that? Okay. So what it is a program that's got a bunch of calculators all in one. It's got PCB calculators. It's extremely useful, and it can tell you, by if you've got a certain weight of copper, thickness, wideness of trace, what the resistances are. It can tell you the resistances of vias connecting through traces. It can work out strip line impedances for you for a given type of FR4 that you're using. So if you're designing PCBs and you're wondering how much current can something take or whatever, then that program's really useful.
What's that called again?
Saturn PCB Tools. It's by a company called Saturn, called PCB Tools, and it's free, which is
You're going to
even
demonstrate it next week.
better. Yeah, I'll show you a quick show of that.
Thanks, Tom.
It's all right. I mean, I don't even use a quarter of the tools on that program, because it really is for PCB designers. There's a lot of stuff on there, and the chances are you'll just need a few portions of it here and there. What does this mean? Gold fingers. So that is the edge of the PCB. So, like PCI slots or, edge connectors, you put a ENIG surface finish. Oh no.
You can just use it when you put the gold plate.
Yeah, I think that's, you have to specify if it's got those or not. If you've got those features, you have to click yes. Material type, that's mainly, there it says in there, but it's a lot to do with the temperature. Better flame resistance, lead-free assembly.
We should probably go for that flame resistance.
Yeah, and they're also they recommend it for 4 and 6 layer PCBs as well. High precision PCBs, so it's obviously a lot stiffer. It's an extra $3 as well, so that could be a safe option if you're going for quite high reliability. Confirm production file. Don't know what this is. It's complete. So okay, so that's you're getting somebody else to actually check over the Gerbers before it gets made. So for prototyping and stuff, you probably won't need to. Obviously, you've got this checking here, which is really good. But if you get a big design, you know, you'd probably do that. Flying probe test is automatic, so it's pretty cool. This, as part of their process, they've got a flying probe array. Once the PCB's been manufactured, they'll test all of the nets for you and make sure there's no short circuits, and they'll make sure all the nets are connected together as well for free, which is very nice. Castellated holes. That's when you've got a PCB, like imagine you've got a small daughter board PCB that you've designed, like it's got a Raspberry Pi or something on it. If you want to connect that to another larger PCB, you can use these castellated holes, and then you just put a surface mount pad on the motherboard PCB, and then you put the castellated hole daughter board on top of that, and you just solder. You just put chunks of solder along those edges, and the solder wicks up. Do you know what I mean? Does that make sense? Yeah.
It's almost like it's like a through hole in one board, and like it absorbs up into it, and it solders it together.
Yeah, apart from the through holes chopped in half.
Okay.
So you imagine on the daughter board, you've got a bunch of through hole pads, and then you cut right down the middle of them. So the inner of that via there is exposed.
Yes.
So the solder, and that would go onto a pad on the motherboard that kind of comes out a bit like that. So this would essentially be like a chip that sits on top of the motherboard, and then the pads on the motherboard would come out and underneath this part, and you'd put a big blob of solder, and it would connect all that together. Remove order number. If you want to remove the order number, it costs you. You can specify a location for it, because they will just put a number on it somewhere. So if you're bothered about the aesthetics, you can do that. And then that is it. Then so that's it for a PCB manufacturer. So you can save it to cart, get it made, and then it'll be with you in a few days.
What's in the advanced options? Out of curiosity.
So this is tighter toleranced. That'll be testing actual resistances on, I suspect, an extra part of the flying probe test paper between PCBs. That's not the paper you were talking about. Yeah, it's protection. And appearance and quality, I don't know the...
I imagine if you want a custom stack up, you have to talk to them directly or find a different...
Yeah, this, I mean, Chelsea will be able to do it, the massive, but this process I'm showing you now, maximum of 6 layers, you know, relatively basic options. If you needed something advanced making, you'd talk to them or go to someone else as well. So these are predominantly for people around the world to just get boards made quickly and experiment with, and you can put these in production as well. The other cool thing about JLC is they do SMT assembly. They've got a library that you can have a look at, and if you choose parts out of their existing library in the BOM that you've made, then you can check this, and when you do, they'll populate all the components for you. You'll pay for them, but they'll populate all the components and they'll post you a fully populated board. So that is an option where if you just use their parts that they've got in their pick and place machines already, that they've already got set up, and they've got a big library, they'll send you a fully populated board.
Worth it for the SMD stuff?
Certainly for larger boards, for certain types of SMD, BGAs, you have to solder BGAs reliably.
Also, if you did take 80,000 production.
Yeah. BGA ball grid array, it's the chip that's got a bunch of balls underneath it.
Yes, yeah.
You can't even get your solder iron to them.
You have to use like a reflow or hot air.
Yeah. Exactly.
Can you get it like semi-populated? Say if there's a small range of stuff that you can...
Don't know. Yeah, I'm sure actually. Yeah, I don't know.
The parts that are not in the library won't be placed on your board.
Yeah, so it might have to be it might be the case that only the ones that are not in their library.
I suppose you can sort of cheat it then.
You could.
All right, that's good to know.
Yeah. Pretty cool that.
And then that's a stencil.
The stencil. So that's if you're doing a panel, and the stencil costs. I mean, you're paying $7 for a stencil. So that's a laser cut piece of probably mild steel or aluminium or something that you can use to put the solder paste on. They all come in like standard sizes. And if you're getting a panel made and you're getting it all assembled somewhere, $7 for a stencil, it's just such a good price.
Do we have a frame?
At the moment, no. James was showing me his setup that he's made, which will work, but I think he's looking at a frame. Did you guys buy a frame?
No, I don't like stencils.
Do you not?
They're very unreliable because at least the cheaper ones, they're quite a thick piece, so once you put the solder on, it leaves loads on there. You put a component on, it just
Swamped it.
And I don't like it.
Okay.
I can't get used to it. And I can't get the consistency that I can.
Have you got a proper frame?
No, not that I know of anyway.
Okay,
But
that would
we've got
help.
a brand new machine now. So.
Yeah. Having a proper frame would certainly help that process.
Yeah. It would be good if you were to have some way to actually put it in and have the right fixings for
Exactly.
each board.
Exactly. That's kind of it's an important part of it. But James has set up something that I think will work quite nicely.
Just the boards in an array
Yeah.
around it.
Yeah. Cool. Right. So that's essentially how you do it. You click Save to Cart. You go to the checkout, log in, and everything else, and then you pay for your boards, and then the boards will arrive in the post. And these boards will arrive today. So I'll be checking those out later.
I hope they're purple down.
Well, maybe. Let's go back into here. That one. Cool, right. So things to just kind of keep in mind when you're doing this process. Print the design on paper, like I said. Print it. Definitely print it. Always print it. And then you'll see whether you've made any blinding errors, or even errors that are hard to notice without seeing it in person. Generate the Gerbers to the supplier's spec. I had to do that 3 times this time today, so I'm sure you'll do better than me. And then carefully consider the PCB options. So if you don't understand an option, then go and do a bit of research and find out what that option is, find out what it means, and then you're confident in yourself that you know that you've chosen the right things when you're making the PCB. You can send me the boards and layouts if and when you get to this stage. I'm happy to review your boards and your layouts. Obviously, I appreciate 2 things. One, to get to this stage is actually a massive amount of work for people who aren't just very familiar with PCB design. 2, we've all got other jobs to be doing as well. So if at any point, in the future, you come back to this and you want to get to this stage, you want me to review it, I'll review it, and I'll help you get through that.
Review.
Appreciate it. Yeah. So Joe will help as well. Right. So all going to plan. I'll put on a practical demonstration. I'll bring a scope in, and I'll try and get the cameras set up and do some stuff, and I'll try and get some audio thing working, and we'll do some experiments, and we'll understand. This is like not Proteus, okay? This is like off topic, but it would be a nice finish to this series, I think, and I think it will be quite interesting. And then you can come and have a play. You know what I mean? Just mess around with the setup. The setup that I'm going to have is really simple. It's this. I've got a sound card. Oh my god, that's going to sound awful on the video. I just knocked it over. I've got this sound card. And I'm going to be using, this sound card in particular has got quite a good distortion characteristics, it's got good recording characteristics, it's got a 24-bit DAC, and it's about 100 odd quid, so it actually wasn't like mega expensive. You can use it, but you can use any sound card that's got an output and an input to carry out fast Fourier transforms and the stuff that I've been showing you. 3.5mm cables to connect stuff together, obviously the headphone amp that I've not included here, and then software to do the FFT for you. Both of these bits of software have got trials. You can even do it at home. Once I've shown you how to do this, if you're interested in experimenting with this kind of stuff, you can do it yourself. Just to get a quick sneak peek, this is an FFT that I was running on my hardware in particular, and at this point I was injecting a 8.2 kilohertz signal, total harmonic distortion of 0.003%, and then as I increase the frequency, you see all this really bizarre interactions going on. There's a huge filter. This filter here, I think, is a digital filter, and I'm clipping the voltage. The voltage is clipping ever so slightly at that point. So there's definitely something odd going on there. But when you see this in real life, you can see these transient, these features sweeping up and down the range, sweeping up and down the spectrum. So you'll see. Yeah, it's interesting. Okay, so that's all for today.